today we are pleased to have Dario from TU Berlin. He's a PhD student. We talk about well-quasi-ordering directed graphs, right? Eulerian directed graphs by Immersions. Yeah, please.
Yes, so thank you for having me here. As you said, my name is Dario, and I'm a PhD student with Stephan Kreutzer, and I'm going to report to you on recent progress that we made on well-quasi-ordering Eulerian digraphs by strong immersion. This is joint work with Ken-ichi, Kawarabayashi, and Stephan Kreutzer, my PhD supervisor. Before I start the talk, let me tell you what the goal of this talk is. The goal of this talk is to convey an intuitive idea to you guys about what we are doing, to an extent that I hope that everybody will think that everything we did is trivial and you can go home and do the same thing without me giving you any details. Okay? So that's the plan, and I hope we'll manage that. So I have a lot to talk about, so let's dive into some basic definitions. So first of all, what is a quasi-order? A quasi-order is just a tuple where you're given a set and a binary relation that is transitive and reflexive. Right? So for example, the natural numbers with being less or equal, or maybe natural numbers without 0 and being a factor. Right? So for example, 1 divides every number, 6 divided by 2, and then 12 by 6, and then basically it's transitive. Right? It's pretty easy. And then if you think about graphs, for example, it would be the finite set of trees together with being a topological minor. Right? The tree is contained in another tree as a topological minor if you can find it as a subtheorem. Right? And then you can convince yourself that this also is a transitive relation. Right? And maybe another relation that you guys may know about is just being graph minors, where a graph is a minor of another one if you can get it by taking subgraphs and then contracting edges. Okay, so these are examples of quasi-orders, and then we call a quasi-order well-quasi-ordered. If for every infinite sequence you give me, I can tell you there's some element that after that element, there's another element where the first one is contained in. Right? It's like forward contained in a sense, okay? For every infinite sequence. So this is equivalent to saying that you don't have infinite strictly decreasing sequences. So if you get smaller and smaller, you will reach a minimum. And also there are no infinite anti-chains, so infinite sequences where you have pairwise incomparable sets. If you take, for example, the second example, and then that's not a well-quasi-order because prime numbers, if you take the sequence of prime numbers, it's infinite and nobody is divisible by the other, right? So that's an example of something that's not a well-quasi-order. Turns out that the first, the two obstructions, the first one is almost always true if you work with combinatorial quasi-orders, just by the pigeonhole principle. The thing is that if you think about infinite strictly decreasing sequences, what would that mean? For example, if you talk about topological containing trees, if you're strictly decreasing, right, then the first tree has some number of vertices, let's say 10, then the second one needs to have at most 10, right? So at some point they have the same number of vertices and then they are basically isomorphic. So and the same is true for being graph minors, right? You have to get smaller and smaller, and at some point you reach isomorphism, and then so you don't have. So most of the time the first part is free. You don't have really strictly decreasing sequences. So we care about, do there exist infinite antichains? So that's basically what we need to figure out, right? And the thing is, why should you care, right? I mean, why should you care? And I will postpone the answer, so I will not give it here. But one reason is it is fun, right? You can just ask the question and think about it. So, okay. Before we discuss why should we care, I'll give you some results that are pretty important for what we are doing. And the first one being due to Kreutzer in 1960, who proved that the class of finite trees is well-quasi-ordered by this topological containment relation. So it is well-quasi-ordered. And Kreutzer actually proved something stronger. He proved that you also can assume that your vertices are labeled with colors that come from a well-quasi-order. Right? Nash-Williams then forgot about this well-quasi-ordering labels, and he just took the proof of Kreutzer and gave us a better proof, not a better proof, but a way simpler proof that proves that trees are well-quasi-ordered by topological containment. And this proof, due to Kreutzer, is very important to us because it basically is a fundamental building block of how our proof works, or generally it proves that you know about well-quasi-ordering. So I will take the time to sketch to you the proof of Kreutzer, again without real details, but I hope you will take away the whole proof. Right? So what do we do? Well, how do you prove this? Well, you assume it's not true, right? So what does it mean if it's not true? If it's not true, it means that we find an infinite anti-chain, because it's not well-quasi-ordered, right? So now we choose an infinite anti-chain in a way that we choose the first element of that anti-chain as small as possible, such that it is the first element of an anti-chain. You just take that one. And then you choose the second one with respect to the first one, saying, okay, now this one is so small that the two basically are as small as possible, such that they form the start of an infinite anti-chain. And then you continue with the third one in the same way. You pick them as small as possible, and then you build an infinite anti-chain. That's where every first I elements are as small as possible to being such an anti-chain. Now the idea behind this is that, well, if you look at these subtrees, we'd hope that, okay, they are smaller. hopefully they are well-quasi-ordered, right? And the thing is, well, this is true, because let's just look at the subtrees and take a sequence of subtrees. For example, this one being like T21, so this would be this tree, right? And then you take T41 and T67, and you assume this would be an anti-chain. Well, then you could just put T1 in front, and now you have a smaller sequence that's an anti-chain. Why? Because, well, T1 cannot be mapped into any of these. Otherwise, it would have been possible to map it in one of the trees already here above. So this cannot happen. So the subtrees are indeed well-quasi-ordered, right? So this would basically be a small anti-chain, which is contradicts your assumption. So they are well-quasi-ordered, the subtrees. Well, that's good. How can we use this? Well, the hopes would be that not only are they well-quasi-ordered, but we find two trees such that the subtrees of one tree can be mapped into the subtrees of the other tree, and then we kind of can lift it, and then we have a contradiction to them not being well-quasi-ordered, that the chain was bad. And this is not only hopes and dreams, but actually, what we need now is, when you try to do this, you realize that you need your trees to be rooted. Because if you want to lift this tree, then you sort of need that this guy has a path up to the other, right? So that's why they prove it in a rooted setting, okay? So you realize while doing the proof that you actually need to do it for rooted trees, which works out. And it turns out that this is not only hopes and dreams, but we can actually guarantee this, which is also a really important theorem, which is why I give it to you. It's a theorem due to Higmans. So the theorem states that if you have a well-quasi-order, just think about it as colors where shades mean inclusion, right? I give you well-quasi-order. Then Higmans tells you, well, if you now take a sequence of finite sets of these elements, they has to be finite, then basically you can guarantee that you find a subsequence that's infinitely long, such that now you have an injection in these maps. So you have an injection that goes from x1 to x3, you have an injection from x3 to x5, such that the elements now respect the well-quasi-order. So basically you can map colors to the right colors, right? And Higmans now tells you basically that, okay, you can get these maps. So in our setting, this means that, well, if we take the subtrees, and they are well-quasi-ordered, then they form basically such sets. So now we actually can get a map that takes one tree, take all the subtrees of one tree, all the subtrees of the other, and finds an injection that maps subtrees to subtrees. So now basically we can guarantee that we find such a tree that maps all its subtrees to subtrees of another tree, and then you can lift it with the argument that we made before. Okay? Again, don't worry about details. This is the general idea, and you can think about it more easily as follows. Namely, what they actually do, and what we will need as a black box, is the following. Assume you have a counterexample that's as small as possible. You can find smaller pieces that are counterexample. What you do is, well, you decompose it in some way. Now you have smaller pieces. These smaller pieces, because they are smaller, as we've seen, they are well-quasi-ordered. Now you use Higmans' theorem that tells you, okay, well, if they are well-quasi-ordered, then I can map all the pieces of one guy into all the pieces of another guy, respecting well-quasi-order. So in the last step, all we need to do is we need to glue these pieces together, and we have refuted that this was a bad antigen. So if you don't want to think about counterexamples, just think about this being an inductive procedure, where given, if you know that pieces are well-quasi-ordered, you can glue them together to produce bigger well-quasi-orders, right? Now this whole black box is basically the foundation behind what Robertson and Seymour did to prove that undirected graphs are well-quasi-ordered by the minor relation. They took this and basically perfected it. This whole black box idea, they wrote 20 papers to prove this, introducing the whole graph minor structure theory, which essentially gives you these building blocks. It tells you can take your graph and decompose it into pieces that now are well-behaved, and they are well-quasi-ordered, and then glue stuff back together to produce a well-quasi-order. So they go through this black box. And if you have not read this, this is the most beautiful piece of art that I've seen today. I mean, it's a painful read, but it's also joyful and really rewarding. I haven't read all of them, but a lot. If you haven't, do it.
So you meant you read, really?
Yes. Well, not all of them, but it's really beautiful.
Okay.
Okay, so they basically used this technique to prove that undirected graphs are well-quasi-ordered, and they established all this, how do you decompose graphs and glue them back together, right? And then they went on and they didn't only prove this, but from it derived that undirected graphs are well-quasi-ordered by weak immersion. Now what is immersion? Immersion is basically the following. You have two graphs, and one graph immerses in another graph, so it's contained in another graph. If you have a map that maps the vertices of one graph into the other graph injectively, and then it maps edges between two vertices to paths with the same endpoints, such that the paths are edge disjoint. So you basically map edges to paths, and then the paths need to be edges joined. And we call such an immersion strong if you have two edges, then no path uses, so it maps to paths, and no path has as an internal vertex an endpoint of another edge. Right? So you basically want the terminus of the edges to kind of be free in the sense that nobody uses them to run through. Okay? Then we call this a strong immersion. So the thing is, if you don't allow for this, like it's a weak immersion if you don't require this. So if you allow for edges to be mapped to paths and other paths can route through the terminals of the path, then it's called weak. And Robert and Seymour proved it for the weak immersion. I want to note here that if you think about immersion, then it needs to respect degrees. So if I take a degree 4 vertex, I have to map it to a vertex and all its edges to paths adjacent to that vertex, so it has to have at least that degree, right? You have to have at least that degree. And this is the main problem why basically their proof doesn't extend to strong immersion. In fact, it's still open for strong immersion, as far as I know. And these high degree vertices are basically also, as far as I know, the problem for why it's still open for bounded tree width. Now, correct me if I'm wrong, but as far as I know, it's not known for bounded tree width, unless you have bounded degree. Okay, so now the question is, okay, these are all like known results. What do we do with it? Now you could ask yourself, okay, that's nice. What about directed graphs, right? I mean, they all did it for undirected graphs, so that there's nothing much to do besides the strong conjecture. You can ask, what happens with directed graphs? And directed graphs are kind of strange. See, most of the things just don't work for directed graphs. And basically every I talked to you about different parameters, immersion, graph minor, topological containment, and all of them kind of are well-quasi-ordered. And for directed graphs, things just don't work. Almost every containment relation that is well studied for directed graphs turns out to not give you a well-quasi-order. Where, for example, immersion for directed graphs is defined in the same way as for undirected graphs, except for directed edges are mapped to directed paths. Okay, that's the only thing. And it turns out that this doesn't give you a well-quasi-order. So immersion doesn't give you a well-quasi-order for directed graphs. And here's a counterexample. You basically take something that looks like a path, but it's like alternating edges, right? You go once to the right and then to the left. And then you continue this to a growing sequence, right? Where you basically alternate edges after edges in direction. This gives you a long sequence of alternating paths. And then you kind of mark the outer vertices of the path to be degree 3. So now you have alternating paths with the outer vertices marked by being degree 3. And I told you immersion respects degrees. So we are forced to map these degree 3 guys to degree 3 guys. Just because that's the way immersion works. But then there's the middle guy that has to go somewhere. And wherever you try to put it, you will not be able to find directed paths. You will not find directed paths just because there is no path because they are alternating. You cannot drop through. So this is an anti-chain. If you grow, then you cannot map anyone in anyone. And so directed graphs are not well-quasi-ordered by immersion. Not weak, not strong, either. So that's frustrating. And you could ask, well, okay, are there classes for which this could work, right? I mean, could still be nice classes that have a lot of structure. And actually, I think Seymour and Chudnovsky proved that this is true for tournaments, which is, as far as I know, one of the most versatile directed classes for which this is known. And there's another class that's particularly fruitful, which was the title of the talk, and it's Eulerian digraphs. Okay? Now, these are directed graphs with one specific condition. All the vertices satisfy, they have equal in degree as out degree. That's the only restriction, right? And you could ask, okay, well, are they well-quasi-ordered? Since they are almost like undirected graphs. They are really close to undirected graphs. They share a lot of similar properties. For example, I don't know if you know Menger's theorem, but there's an analog of Menger's theorem for Eulerian digraphs that really fits the undirected setting in the sense that you have paths in both directions of a cut respecting direction that's completely disjoint, where this is not true for general directed graphs. I'm not going into the details, but let's just say they behave very similar to undirected graphs. So they feel like a good candidate because they are similar to undirected graphs, and it's true for undirected graphs in a sense. Then let's try and prove that they're well-quasi-ordered. And there's one easy trick to make every digraph Eulerian. You just put a big vertex on top, and you connect everybody that's missing some in degree or is having too much out degree to that vertex to fix it, so that every vertex has the same in and out degree. Then the resulting graphs will be Eulerian, just by having this guy that basically takes care of all the deficits. Right? If somebody's missing out, then it has an edge. Somebody's missing an in edge, then it's getting something, and this turns out to be an Eulerian digraph. Whichever digraph you give me, you can construct an Eulerian one. So now the problem is, I told you that immersion has to respect degrees, right? So this big guy has to be mapped to the big guy. And if you have strong immersion, then basically we are dead because nobody can use this guy to route through. So now we are left to map the lower guys into the lower guys, and I already told you that doesn't work. So basically, Eulerian diagrams are not well-quasi-ordered for strong immersion. So thank you very much, and we failed. So no, that's not where the story ends, right? It's just we didn't. So they are not well-quasi-ordered by strong immersion. Okay, fine. But you can ask, okay, but maybe it's just because of this big guy, right? And that's actually the conjecture. The conjecture is if you bound the degree, if you don't have this one big guy, but you're in a class of bounded degree, then it is well-quasi-ordered by strong immersion. And this was already conjectured also by Johnson, but he never published any proofs or steps toward it, but we will talk about it, something that he did later. So this is a standing conjecture, and we think that we have a proof for it. So before I give you the proof, let's talk about some implications. Because remember, I asked you, why should we care, right? Now I tell you why we care. So first of all, this gives us an easy way for containment testing. We get polynomial time containment testing. What I mean by that is the following. So with the same group of people, we proved, it's part of this project, we proved 2 years ago that deciding whether you have edge disjoint paths in Eulerian digraphs is FPT. Okay, you can solve it. You can solve it fast in a sense, and this yields that if you give me two graphs and you ask, can I immerse one strongly in the other, if they are Eulerian and on the degree, then you can decide this in polynomial time on the first graph, on the size of the first graph. So now, therefore, if you give me a property P of digraphs that's closed under strong immersion, so if one has it, then everybody that's strong immersion of it has it, and you take the class of Eulerian digraphs of maximum degree delta, then well, you can decide whether your graph has this property. And you can, basically this follows from being well-quasi-ordered because, well, you just define the set of those graphs that don't have the property and are minimal. Minimal meaning that everybody that's smaller with respect to immersion has this property. Now this class is well-quasi-ordered, so it has to be finite. So there's only finite obstructions, and we can test each obstruction in polynomial time. Okay, so again, no details, but basically that's where you get.
Is this FPT or not?
So no.
No.
This no. But for every fixed age, it's kind of they're fixed. Yes, it's not because we didn't solve folio. Yeah. Okay. Now there's a second implication that I will not talk much about because I think there's people in this room that know much more about this than me. It would yield that circle graphs are well-quasi-ordered by pivot minors, which, as far as I know, correct me if I'm wrong, is still open. Okay, so it would imply that. If you have any questions about this, you know who to ask. And then we also get further results. Basically, on the way to proving this, we get structural graph theory results regarding Eulerian digraphs, such as Elish-Posa results or other things. Okay, and then there's a second conjecture. Let's say we have this big guy. Okay, we're not well-quasi-ordered by strong immersion, but there's a conjecture that says, well, we conjecture that we are by weak immersion, right? Because remember, well, if you have these guys, then the big guy needs to be mapped to the big guy. But there's a lot of free edges left. And if we are allowed to route through there, then maybe there's hope to use it also to route the rest of the graph. And we claim that this is also true. Okay, then we can prove that this conjecture is also true. Okay, now, what is this talk actually about? What I want to show you today, or what I want to convince you of today, is the following theorem. If a labeled version for the first conjecture, where you fix the degree to be 4, is true, then everything's true. Then both conjectures are true. Okay, so basically I will convince you that it suffices to look at degree 4 with some restrictions. And then everything's true. Both conjectures. Okay? That's the goal of today. Let me mention that we already proved that for degree 4, if you can embed your graphs in surfaces, then everything works out, and they are well-quasi-ordered. So there's one step missing that we can discuss at some other point. So we will talk about basically this reduction. Okay? That these conjectures are true if you believe me that for degree 4 we can kind of solve them. Okay. How do you prove such a thing? Well, and now comes the part where I hope everybody will, after the rest of this talk, go home and know how you prove such a thing. So imagine you want to prove conjecture 1. The class of Eulerian digraphs of maximum degree delta is well-quasi-ordered. If you want to prove it, you can assume that it's true, right? So let's assume, we want to prove it, so let's just assume that it's true because that's where we want to go to. So assume it were true, then actually what we prove is whenever you give me a sequence, I can map someone into another one. Now take a sequence and assume that some guy is not part of the sequence. Some Eulerian digraph is not appearing there in that sequence, right? Just by, for example, cutting out an ideal by filtering in the well-quasi-order. Then, if I now take my graphs and I somehow add this guy to it, it's still Eulerian, right? But now I am forced to map these R guys into the R guys. Because where should they go? I know that they are not part of the sequence. So this way I kind of can force who goes where, right? And this is basically like just coloring these vertices with the type of the guy that I was lacking. So if it is true, then it should be true that a version with a color on vertices is also true, where we can fix some guys. And you can extend this idea to say, well, if this is true, then it should also be true when we use a well-quasi-order on the vertices, like colors on the vertices. Okay, this is a much stronger claim that should follow from the actual claim. Like it should be ideal. Like there's some details, but it should follow from it. Now you can ask why should we do that? Right? I mean, it's a harder problem. Now we have colors on our vertices, and the reason is because of induction. You know, if you do induction, often you need stronger assumptions, and this will help us a lot by induction. So the first thing you notice is that if this is true, then it should also be true with colors. So what we will be looking at is graphs with colors. And then we want to apply that technique that I told you, like the induction technique. So you take a minimal by sequence, and then we want to decompose it, then we want to use Higmans, and then we want to glue, right? Remember? Now the first step is decomposing. So how do you decompose graphs? So we're working with strong immersion, so the natural way to decompose is at cuts. Because we want to inductively know it's true and then glue our results. But strong immersion doesn't allow you to go through vertices that you already used, so we kind of want to sort them aside and never use them again. It'll be like, okay, if you have something already going on, then we don't want to interfere with it. So we kind of want to decompose our graphs at cuts. Now, let's assume now that we have in our minimal bed sequence, everybody would have like a cut of size 4, like 4 edges. If you are Eulerian, that's basically you get even cuts, and you have that cuts have as many edges in one direction as in the other direction, right? So assume now we have in our sequence these small cuts, everybody has a cut of degree 4. Then the idea now would be that, okay, well, we just contract the upper part, we contract the lower part, now we have 2 pieces, and they are Eulerian, and they are smaller. So these pieces should be well-quasi-ordered, so they, by induction in a sense, so this is kind of where we want to go, right? Now, what would be the next step? Well, the next part, so yeah, they are Eulerian. The next part would be, well, now we have these guys, we want to map them into each other using Higmans. We assume they are well-quasi-ordered by induction, so let's try to map them together. Well, we realize immediately that if we want to do that, later we will want to glue, right? So we kind of have to make sure that this guy here is kind of mapped to this guy, and that the guy above it is like, this blue guy is mapped to this blue guy, so that the cut edges can later be reconnected, right? So that's why we will also want to make sure that cuts are respected. Okay? So now let's assume that our induction just does that. Then we kind of can glue back together. And then we are done, right? Almost. There's a problem. Because imagine these are the 2 upgoing edges, right? And after I contract, I map them into each other. Well, it may happen that somehow we messed up the order. So now basically the bottom orange edge on the bottom is mapped to the left one, but the orange edge on the top is mapped to the right one. So now by gluing, we wouldn't produce the actual graph, we glued the wrong edges together. So that's why we need to keep track of a linear order on the edges and vertices. Okay? So basically what this tells us is that if you have a cut, what we will assume is that in induction, these cuts will have linear orders on the edges. So basically, think about them as colored edges. And then we will guarantee that orange edges are mapped to orange edges and red edges to red edges. Right? So this is something that we will have to take care of. And then now, if you then do the decomposition, then you really get that the right edges are mapped to the right edges, and you can glue the stuff. Okay. So that's one thing we have to take care of. There's another one. So imagine you want to do that induction, and you kind of want to use induction, so you add your pieces, and then you know that your pieces map into each other. And then you later want to glue, right? Now, what can happen is the following. Remember this guy from the beginning, especially the middle guy. This is called a swirl. It's just cycles that go in opposite order. It doesn't matter too much. So imagine you'd have this guy in your graph. The red one is a graph. We have a small cut, and this guy is sitting there, right? So if we would decompose at this cut, if we would put this into 2 pieces at this cut, then the swirl would basically become, we would contract it into a vertex, right? Okay, now let's think about how can paths use this thing. So if you give me paths and you want to connect them, right? Let's assume this will be clear in the next picture. Let's assume you'd have paths and you would want to connect them. Then the topology of this graph doesn't allow you that. The topology of this graph doesn't allow to connect the orange guy to the orange guy and the blue guy to the blue guy. So this means that there you couldn't cross, right? You couldn't realize these, okay? So if I now go and I've done my induction and here are some pieces that I cut out, then all of them could have been swirls. They could have been this weird guy. So if I now have an immersion of H, then well, in the induction, the immersion may use, like the paths may use these vertices, right? They may use these vertices. Why shouldn't they? They are vertices. But there's the problem that maybe this wasn't allowed. Maybe this was a piece that didn't allow this routing. Maybe we couldn't do that, right? So somehow we have to keep track of that. So every vertex will additionally come with a list of feasible routings in our induction. Okay? And there's one last thing. Namely, this is also a thing. Imagine we have by induction, we have some path that goes through the same vertex like twice, right? Normally you would just reroute. But we may not be allowed to reroute because this may not be feasible in a feasible list. Imagine a lot of other paths using this vertex. They used to sit some graph and he may not allow to do that. So we will not be able to use paths when using immersion, but we will need to use trails. Right? We need to allow that we see the same vertex several times because we cut out stuff and then it has to keep track of how we actually use that graph that we cut out. Okay. Now one can discuss. To me, in our setting, there exist only paths. You may call them trails. Okay. Okay. We are done with what we need. Let me summarize. What are we using in our induction? Well, basically, all we are using is we have graphs that are Eulerian. They have colors from some well-quasi-order. We root them. Think of a big vertex. That's just like the routing, like in Nash-Williams. Think of a big vertex that also fixes how it was cut out. Fixes a cut, an order on the cut. Well, and then we have every vertex comes with a linear order on the edges. And every vertex tells you who is allowed to pass through it. Okay, you will not need to remember all the details, just this should show you there's a lot that we need to keep track of when we talk about pieces. Our pieces will look like this. It's not only graphs, it's graphs with a lot of stuff. Okay? And then basically it looks like this. It's a horrible, horrible big tuple. To write down in LaTeX, it's a pain. But that's basically what it is. Okay, and of course we would need to adapt the notion of immersion to keep track of this, right? Because now we have a different structure well. Okay. So, now we can start to discuss what's happening. Okay, remember, what did we want to do? We want to decompose a graph into good pieces. It's still the same goal, right? We want to decompose it into good pieces that we glue. And we want to somehow use it with this black box that I told you, with decomposing pigments, glue it. So the way to do this is we want to somehow find a tree-like decomposition of these kind of objects. We kind of want to remember the trees of Nash-Williams where we had these subtrees that mapped into each other and stuff. We kind of want this for our graphs. We want to decompose our graphs in something tree-like such that we then can use this toolbox. And this tree-like structure is what we will call C-rippings of order K. What is a C-ripping of order K? Again, you can forget about that. If you fell asleep, just forget about everything and we can start again here. So what is a C-ripping of order K? So basically, it is you take a graph, and then you have a tree with respect to that graph, such that, well, at first, if you know the word tree cut decomposition, it's basically tree cut decomposition, so your bags partition the vertex set. So you kind of start sorting vertices into bags, and every edge basically gives you a small cut of order K. So every edge that you have just tells you a small cut in your graph, right? So this is basically tree cut decomposition in a sense. But now what's basically new? Well, we want more from it. We want that if you look at one bag and you look at it closely in your graph, then it looks kind of like this. This is a partition and these are the other partitions. Then you want to contract these, and then we call it a torso. We just contract and we keep track of the cut. And then we want that this torso basically will be part of this class. Okay? So what this means is that, well, we are in this weird setting, right? And now it will become apparent what we needed. So what we do is, well, we first add the roots, right? That's the root part here. We add a root and just saying that, okay, the guy above me with the root set, I will mark this with a root to remember where am I sitting in the tree. It's the guy above me. Then the next thing you need to do is, well, these cuts, there's cuts of order k, but you kind of need to mark the vertices here with a linear order that kind of keeps track of that afterwards you can glue them in the right way. Remember, we wanted to glue the right edges back together. So here we will need to fix the linear order on the edges so that we can glue in the right way. And then finally, for every vertex, we also need to keep track of, well, how are we allowed to root in that piece that we cut off for the induction purpose. So we will mark this vertex with all the feasible routings. Okay, and then we will allow to add colors. Because in the end, we will want to use induction. So we will want that this is by induction well-quasi-ordered, and this is well-quasi-ordered, and this is well-quasi-ordered. So they are some color. And we want to add that color here so that we keep track of which guy did we cut out. Basically keeps track of the guy that we cut out. Okay, this torso, if that guy is in C in the class that we're talking about, then we call it a C ribbing. So all this is, again, saying is that we have a tree decomposition in the sense it's not really a tree decomposition, but tree cut decomposition where every torso is in a specific class.
Is this for digraphs or for graphs?
You can also do it for general graphs. This works for, it's basically just defined on the cuts, right? You could also define this for undirected graphs. It's just because, yeah, we can discuss some of this later if you want. Then you call this a C ribbing order K if the torso is in some class. Okay? Again, the details from here, I just want to give you the details, these small details, but you don't need them. Just think about it's in some class, whatever. So what do we do now? Well, now we can go back to Nash-Williams, and we have the following. If we have a class that is already well-quasi-ordered, and we have a bad sequence, or any sequence, that admits such a ripping that I just told you into pieces that are from that well-quasi-ordered class, then the sequence was already well-quasi-ordered. So this gives us this leveraging of if you can manage to get a tree-like decomposition into pieces for which you already know that they're good, then everything's good. Okay, that's basically that's one thing that we are proving. That's one main theorem basically of this part, and I'm hiding many details. Like there's a lot of assumptions on these ribbings and the pieces that you have and so on and so on, but you don't need to care. Also, many of these assumptions that I hide are actually where this fails for directed graphs. Right? It works for Eulerian digraphs because they behave similar to undirected graphs. Okay, so we have this meta theorem. So now we can ask for, okay, so this meta theorem tells us, I give you a class. If you can decompose this into good pieces, then we are done. So there's a question for, okay, but what are good pieces? And one thing that's easy is that, well, the pieces that have not many edges or vertices. If you have finitely many, then you can show, as I mentioned in the beginning, this is like a combinatorial stuff, like a combinatorial relation. So they will be good pieces. Now this immediately gives us basically that, well, if you have bounded tree ripping, however you define it, then you are well-quasi-ordered, right? Because if you can put it into pieces that don't use many edges and vertices, then they are well-quasi-ordered. Now you can lift it. So this basically solves with some assumptions, the bounded tree width case. It's not really, it's bounded tree within if you have bounded degree. Okay. So now we know that if you have bounded ripping in a sense, then you are well-quasi-ordered, right? Because we know that these are well-quasi-ordered. If you have bounded ripping, you're well-quasi-ordered. So you're left with, well, who's not in this class? That's a big, you're left because now we get to structure theory. So you're left to decide, well, when can I not rip graphs into good pieces, into pieces of small size? See, and here you basically need to think about first, okay, if you want to think about structure theory, you kind of want to find what are universal graphs in your setting. What I mean by that is, what is a graph class that immerses everything in a sense, right? Like cliques. Cliques in the undirected setting, they have everything as a minor in a sense. If you are in degree 4, for Eulerian digraphs, it's basically routers. We call them routers. It's sets of edge disjoint cycles that pairwise intersect. if you have such a thing that's big enough, then you basically can immerse everything in it. That's degree 4, right? This is degree 4, so in the degree 4 case, if this is huge, then every degree 4 graph goes in there. Okay? Now, there's a structure theorem by Johnson, and we give a different proof of it in his PhD thesis, and then we adapted and provided a proof more in the context of current structure theory that tells you that if you are not in that class of bounded tree width, in a sense, then you have this guy. Remember the guy? You have this guy as a huge immersion. And if you don't contain a universal graph that's large, then you get some structure. You basically get that this guy doesn't have crosses, like I told you, and then you can lift this to basically like structure theory. You get a structure theorem for regular graphs, where you basically kind of embed your graph and in a particular way. I will not go into too many details, but just telling you that you can now basically decompose your graph into pieces that are kind of well behaved. They kind of look like this everywhere, and then you're basically left to prove that this is well-quasi-ordered in the degree 4 case. I will not go into details, just mention that the structure theorem, there's a weaker version known by Johnson. Right, and then we proved the version where you don't have any extra and you just embed it in surfaces. So this would be the degree 4 case, but I will not discuss this much. What we want to do is to say that if we assume the degree 4 case, what is left to do? Right? So this is the second main result, besides the meta theorem, is we have a structure theorem for being larger than degree 6. So what we need is again a universal obstruction. Before it was these cycles that intersect. Now you have the same thing, but now you have degree delta, right? You have a larger degree, and you still have cycles that intersect. So basically you have many cycles that pairwise intersect, and every vertex is part of delta half cycles. And if you cannot think about this in your head, it basically looks, you get it from this one. Think about just having pairwise intersecting cycles, and then a lot of degree delta vertices sitting around that are well connected into that plot. Then this immerses every Eulerian digraph if there's enough vertices. Okay. So what we prove, and this is basically new, this tool is new, is basically what we prove is that if you have degree larger than 4, like delta plus 2, and delta is at least 4, then there are functions such that either you have such a universal graph as an immersion, as a strong immersion, or you can decompose your graph using this ripping technique, using rippings, such that every piece has only finitely many vertices of large degree, larger than delta. So what this tells you is that, and you have a maximum degree that may be a bit bigger than delta plus 2, but what this tells you is that if you have degree delta plus 2, then you can decompose your graph into pieces that only have a few vertices of degree larger than delta. So you reduce the degree by 2, in a sense, right? You basically reduce the degree. And so you could use this to basically at every step, if you're at degree 8, then you can reduce, and either you have a universal guy of degree 8, or you reduce to degree 6. If you are at degree 6, either you have a universal guy of degree 6, or you reduce to degree 4, right? That's basically the induction that we will use to basically leverage the degree 4 to the larger case. And it turns out that this basically is a complete fine-grained classification of the structure when you exclude a fixed Eulerian digraph as a strong immersion, right? Because it really takes care of the degrees, right? I'll talk about this in a second, but we are pretty convinced that an analogous result should hold in the undirected setting, where you reduce the degree by 1 and you end with degree 3. But what I want to stress is that there are already structure theorems for strong immersion. There's, for example, one particular strong one from Vollen and Vorag, where they basically give you a structure theorem if you exclude some large clique as an immersion. Now, why is this different? Well, if your graph has maximum degree 3, then you have no large clique as an immersion because it has to respect degrees, and there's no large degree guys. So it doesn't help you as soon as you bound your degree. It only helps you to bound the degree, but as soon as you are in bounded degree, you will not immerse large cliques. There's no way to immerse large cliques if you have degree 6. So this takes a step further and then analyzes the structure as soon as you have bounded degree. Okay? Okay, now we are done. Now we can put things together and get the proof. So you're almost free to go. Okay, so how do we put everything together? Now assume, I will prove, like give you a sketch of conjecture 1. Assume that you have degree that's at least 6. And assume we know that degree 4 is true, and by induction we proved it for degree up to delta, and we want to prove it for delta plus 2. So you take a bad sequence, so assume it's wrong, take a minimal bad sequence, like Nash-Williams. Well then, if you take the first graph, right? If you take the first graph, say it has 10 vertices, then the graphs later in the sequence cannot immerse a large universal graph, because otherwise you could immerse it into it. Right? So basically, if you would found a large router, then the first guy would immerse in it, and then this wouldn't be a bad sequence. So you don't have these guys. Now, we just saw that if you don't have these guys, you get a ripping into pieces that only have a finite number of large degrees, and everybody else has degree delta. So you get from delta plus 2 down to delta. So now we are left to prove that this class is well-quasi-ordered. So what we know is, if we only have delta, we are well-quasi-ordered. But now we have a few more guys. We have a few more guys that are well-quasi-ordered, and we need a few more guys that have larger degree that we need to get rid of. So what you do is you take the sequence in that class. You want to prove that it's well-quasi-ordered. Now, it may have some guys that have degree larger than delta. Not many, just a few. What you do is, okay, you filter. You use pigeonhole principle by saying that, okay, well, there are only at most fn of these, let's say 10. Most of them will have the same number of large guys. So you basically have this guy has 2, 2, 2, 1, 2. So you get down to everybody has the same number. And then you can again filter to assure that they have the same number of the same degree. So now we have a sequence where they have the same number of the same degrees. Well, and then you can also assure that all of these guys behave in the same way. They have the same feasible routings. This is also possible because they have finite degree. Okay? And then, well, now what we do is we have colors on the vertices, remember. So what we do is we just add new colors. Here we need 3 colors. We add new colors. We need to add finitely many. There's only finitely guys. We add these colors just to mark who was who. We rip the degrees apart a bit, like we split off to get lower degree, remembering who was who. Now we are in a class of lower degree. Keeping track, we need to keep track of the routings, but let's leave the details. We are in a class of lower degree, so this is well-quasi-ordered. Why? Well, because we didn't care about a well-quasi-ordering. I told you it has to be bigger, so we allow for a bigger one. This is well-quasi-ordered for every well-quasi-ordering. Also with the one where you have blue plus 2 and pink plus 3. So the right guys will be mapped to the right guys, and then you just put it back together, and then you're done. So this class is well-quasi-ordered, and then the meta theorem tells us everything is well-quasi-ordered. So that's the proof, except that I lied. I lied in the first line. There's something wrong. See, so this claim is true. It's true that GI immerses. If somebody immerses a large router, then G1 will immerse in there, right? But we forgot about colors. So what if this guy has only one color? Now we are stuck, right? Because it doesn't have the colors that we need. So this does not really help us. Well, and now I just skip the rest and say you can then basically use another structure theorem where you cut off colors. You can make induction on color. You basically find, if this is not true, then you basically are not, your colors are not well linked into that router, so you can cut it off. You can cut off a color, you reduce colors, and then you use induction on colors. I will not go into the details. And then also I skipped, well, why can we even cross here, right? Well, that's also taken care of by induction. I didn't give you the details. Okay. So the unbounded degree weak case is similar. You will, when you rip the degrees apart, you will basically now get weak immersion. And delta equals 4, I told you, is a special case for itself. You again need to do some different induction. You don't use rippings. You need to do induction on the structure embedding. Okay, that's it. So basically what I told you is that if we assume that degree 4 is true, then we have a proof to lift it up. We are also sure that degree 4 is true. We have a proof. We haven't written it up in every detail yet, but the other parts are basically done. Right? Okay, let me conclude with some open questions. One open question that I'm thinking about, which may be of interest to guys in, especially here at IBS, I guess, is, well, for degree 4, we know that Eulerian digraphs are circle graphs, right? They're like Eulerian digraphs, degree 4 is essentially circle graphs in the undirected setting. I was wondering, okay, but what classes could be degree 6, right? Because if you think about it, if you have a degree 4 regular Eulerian digraph with one vertex of degree 6, it's not so different from a circle graph, because if you delete it, you have kind of a circle graph, right? So how different are they? And if we can kind of get the track of what this is, then couldn't we maybe lift this idea of the ripping theorem to kind of get a structure theorem that basically cuts out undirected graphs into pieces that are circle graphs, for which we now know that they're well-quasi-ordered, and maybe lift this whole technique to kind of get more well-quasi-ordering results for pivot minors. Now this is completely, I don't know, it's just, I don't know, maybe, like, and I would be happy to explore this further. It may be completely wrong, so thanks.
Okay. Thank you very much. Any questions?
Sorry for so much input. We have been too much.
Yeah, fun.
Maybe you're not the one to ask, but can you describe how to derive like the pivot minor result, like from the?
Yes.
Okay.
So, I think I now will be judged, but I think. So there's essentially, if you have a circle graph, and then you get colors. So if you have a circle graph, right, then you have this representation, like, I don't know, something like this, right? That's a circle representation, and then you get a Eulerian digraph from this. There's two ways to think about it. So you always start with orienting this outer cycle, and then either you contract these, you contract the yellow, the blue, and the red guys, or you just, well, you label them being, this is vertex 1, this is vertex 2, and then this is vertex 3, this is vertex 4, and then you kind of construct a digraph from it by taking your vertices, so I don't know, this takes a bit of time, but take your vertices, and then you basically follow the cycle, and whenever you see someone, you put an edge, right? So for example, here you would see 4 and 1, and you basically put an edge between 4 and 1, and then you see 1 and 2, then you basically put an edge between 1 and 2, and then back to 2 and 1, and then 1 and 3, and 3 and 4, 4 and 2, 2 and 3, 3 and 4. So this way you get a 4 regular Eulerian digraph, and it's not hard to see that if you take a pivot minor, then that basically corresponds to an immersion in the Eulerian digraph. Now the thing is that the first thing you'd notice is that if you delete the vertex here, right, then it basically corresponds to just so this comes with a choice of a cycle, right? So maybe I don't have the cycle here, but this comes with a choice of a cycle. And what this would correspond to is that, well, you would split off at this vertex with respect to the cycle. So what that means is that here you see 4, 2. So if you delete 4, 2, then this edge just becomes the edge 3, 2, right? Which is basically the edge that you'd get. And then you do that. So this is basically an operation that's known. It's basically how immersion works. And the second one is you'd need to argue about what happens with, how is it called? Not local complementation? Is it not? No, edge complement. How is the operation called?
Pivot.
Pivot, yes. Obviously, it's called pivot. So, so the way I think about pivot is that basically what you get is you kind of pivot here, which I may be mistaken, but if you think about it this way, then it kind of, if I remember correctly, it fixes the cycle, but it just swaps 2 and 4, right? Somehow. So it would just kind of swap 2 and 4 here, which doesn't really affect something except for choosing a different cycle, and then this is also closed on immersion. And then you'd basically get that if you're a pivot minor, you have an immersion, and so on. Okay. So what is important here is that every configuration is a different, it corresponds to a different choice of a cycle. So the way you immerse would be a different choice of splitting up, like you would have maybe different directions. And then from that you'd get the result. Does that answer the question? Okay. Yes.
So, so the approach doesn't work for directed graphs. So, but if you choose a directed graph of tree-cut width and most bounded tree-cut width, then can you use some reuse?
So, I don't know how the tree, how it works with directed graphs, exactly with the linkness and robustness assumptions. I don't know how exactly the cuts are taken care of, but the main problem is that usually when you have cuts, then you may have the problem of you have a lot of guys going in one direction and just one guy coming back. And what we really need is some sort of linkness assumption that allows you to completely connect these. Not just you can link these and separately link this guy, but it needs to be one linkage. And this, I haven't looked at the details, but in general that just is not the way that directed graphs work. Maybe if you find a class where that works, then you could lift it. Maybe the class that you mentioned does that. I don't know.
Okay, so for Eulerian graph, this part is like automatically.
Yes, due to Menger. So Menger is the main reason why everything works. So what you basically get is, as soon as you have a cut, and the cut is as small as possible, then you will always find a way to completely link this edge disjointly. Right? So you will always find a way that you kind of get, I don't know which way they go here, right? But you kind of get a complete linkage that completely connects these cuts. And then there's the last one. And you basically need this because when you try to lift in the tree, then you need to find paths along which you can lift the immersion. And if at some point you get stuck, so for example, imagine here I have 100 going in that direction, and then I only have 2 that go in that direction, right? Then how should I be able to fit all these 100 paths through this 2 guy? And this is just something that happens a lot with directed graphs. And with the Eulerian diagrams, you can basically get a grip of it. I swept all the diagram stuff a bit under the rug because I didn't feel that it would make it easier. But yes.
Oh, and also like at the beginning of your talk, you mentioned the undirected graphs of bounded tree with the strong immersion case is still open, and then in the middle you said that one of the case that you encounter that it's almost like essentially bounded.
Yes,
tree,
but you have bounded degree.
Right.
So I was always assuming, I may not have been clear about that. The whole part that I discussed was mainly always with bounded degree. If you have bounded degree, then everything works. You can actually prove the strong immersion in the undirected setting for bounded degree, just because they have a labeled version, in a sense. But the point is, what happens if you have unbounded degree? And then it doesn't work. No, it's not that it doesn't work, but then I am not aware of a proof in the literature. I'm pretty sure it should work. But, yeah.
So if the Eulerian diagram has an embedding on the plane where for every vertex, maybe, let's say degree 4, 4 regular Eulerian diagram where at each vertex the incoming, outgoing edges alternate.
Yes.
Then doesn't this well-quasi-ordering follow from the well-quasi-ordering of planar graphs on the minors in certain relation? Or?
So wait, so you say that like this, if you have an Eulerian embedding, and that's one.
Yeah. So in out.
Yes.
In this case.
So
on the plane.
If you are on the plane, then I recently found out that I think you are true that you can somehow reduce this to a version with medial graphs where you can basically apply the medial graph stuff, and then I think it should work. I think this is not true as soon as you start talking about if you are non-orientable. If you, I don't even know if orientable surfaces, but I think as soon as you lift it, it may be true. I'm not sure, but I don't know. Because this somehow needs these cycles, and this somehow needs that you have cycles that see the same number of in and outgoing and stuff, and then I'm not sure how to lift this to general surfaces. But I think that there may be there may be a proof that that can lift that can basically prove the planar case from
by using the well-quasi-ordering of the medial graphs on the plane.
Yes, I actually didn't. So when we put this in archive, I wasn't aware of that result. But I think you're right. I think afterwards I had to kind of review a paper where they said that, I think, and so I was like, okay, sure, okay, I didn't know that. But I mean, it's not so hard for planar graphs. It's not hard. You just you can immerse everything in a swirl and you're done. And if otherwise you have bounded curving with. So there's a different way that's not so hard, but yes.
Any other question? Say, so what is the running time? Like if you have a n vertex graph H, that you want to test whether H is strongly immersed in your.
Well,
What is the exponent?
f of that's I think depending on H.
Right. So
Yes.
there's H.
Yes, it depends on H.
H is
So yes.
and then
So when we proved this result, so it was at the beginning of my PhD, and I didn't know lot like since then I've been mainly reading Robertson Seaborg, right? And because I didn't know that like folio was well, like the main thing that you'd want to solve for algorithmics, right? So we were just focusing on edge disjoint paths, and then the irrelevant vertex technique that we have is not with respect to, it's with respect to fixed terminals. So you get a dependency on the choice of terminals. But I'm pretty sure that you should also be able to prove folio, and then the exponent wouldn't contain H. But we don't have a proof for that, and I think it's true. I'd conjecture that it is true because I think by now I know how one would extend it, or at least how the way should go. But I'm not sure whether yes. I think there's no full proof of it. Sure. Yeah.
So already like Robertson Seymour proved well-quasi-ordered under weak immersion relation,
Yes.
and but that was before the trick up with
Yes.
the notion of trick up with was
Yes.
developed. So with this notion, is there like do you think their proof can be made easier?
So this is touching codes. So yes, and so there's this structure theorem due to Wallen and Vorak that I recently only discovered because again I'm not well versed in literature. I'm sorry, but I recently discovered that, and I think that they basically developed it in hopes to prove it. Right? I think that I'm not sure, right? But I would think that the hope would be to exactly do this, decompose into pieces that are well-quasi-ordered. But somehow there's no proof that it works. So the problem, as far as I know, is that the techniques at this point, again, if you have bounded degree, everything works. It's known that it's well-quasi-ordered. But the problem is if you have unbounded degree, then I think that their proof somehow leaves you with a decomposition where you kind of have huge guys of large degree sitting over a linear decomposition that you somehow need to get rid of. And I'm not sure, maybe they can and they just not publish it, but at this point I think there's hope to use that structure theorem to refine and prove the strong Nash-Williams conjecture, but I'm not willing to go into many details. So I thought a bit about it. I have some ideas how this could be lifted for that, but yes, this project is already very big, so I don't want to spill too many details. I mean, I'd be fine to discuss this, but yes. So I hope there's but again, the main problem is these high degree guys. If you have bounded degree, then everything works out.
Okay. Any more questions? Okay, if not, let's take the speaker.